All right, welcome to Monday. Monday, March 3rd. We're finally into March. Here's what we're going to talk about today. Actually, the big part of the lecture today is going to be on these things called tries, which are actually unfortunately named, but we'll get to why that's the case in a little bit. Here's what we're going to do in a little more detail. We're going to talk about a Unix tip of the day using multiple commands on a single line. There's a lot of different ways you can do it. This is the one I happen to like. Bruce probably can correct me on a better way than this, but we'll take a look at that. Homework 3 is due Wednesday. I know a lot of you guys have been working hard on it, and I'm sorry if it's frustrating, but I'm sure you've got a couple more days to do it. As I said before, if you do need an extension for some reason or another, as long as it's a good reason, you'll probably get it. And we'll talk a little bit about homework 3, and in particular this next free block, which seems to be part of the assignment that's kind of messing with people a little bit in terms of what to actually do in this next free block method. Next week, we actually have a midterm, right? March 12th, Wednesday. We're going to have a review session on Monday. Next Monday will be review. Whole day will be just review and kind of prepping for the midterm. And today we'll go over a couple of kind of test questions, actually questions from previous year's midterms that you might take a look at to kind of expect questions like that. Okay? And then we're going to talk a little bit more about tree operation complexity. We kind of mentioned trees and how they're so great because they're logarithmic complexity. Well, we'll dig in a little bit and see if we can get a little bit deeper into that. And then we'll talk about these things called tries. Some people actually also, the guy who invented this actually calls it a tree, but spells it T-R-I-E. And unfortunately, we have to kind of deal with that. But we will call it a try in here. Okay? Questions before I begin? No? Okay. All right. So the Unix tip of the day. So I've seen a lot of people when I go to labs and help out with homework. I see a lot of people who type things like make, and then they make it, and then they have to run it again, right? And they have to do this whole thing. And a lot of times you want to have a clear screen, so you hit reset before you do that. We've talked about this before, where you can use the up arrow key to do all this stuff, right? You could also, if you wanted to, write multiple commands on a single line. Okay, you can do it a couple different ways. If you want to do reset, actually let me make it so it actually does the compilation. If you want to type reset and then do the make right after that, do a little and ampersand, and that will say do the reset and then do make. Bruce, is this the way you would do it, or would you use semicolon? Right, it will only do the ampersand will only do the next command if the previous one succeeded. Now reset is going to succeed, almost certainly, and then it will make it. You could also do another ampersand and run your calendar as well, and this would do all three of those commands, and it would do it and get the little output there as well, right? So you can do one command, does everything, and checks it. Now, if the make fails, this should actually fail on trying to run your calendar app. Now, if it's just warnings, that won't happen, but if main were to fail for some reason, then we could do that. Like, let's see, if I do nano main.cpp and I type blarg, right, and I purposely fail this. Let's see if this doesn't work. Reset and make and calendar. Okay, it'll try to make it. It'll get all sorts of errors, and then it doesn't try to run it. So that's what happens. Okay. So questions on that? You can use multiple commands on a single line. At some point, I'll do a little tutorial, a little Unix tip on what we call piping. I've seen it before a little bit, but basically having one command feed its output into another command, and you can do this, and it's a very powerful tool when you're talking about Unix commands. In fact, it was kind of one of the killer applications of Unix back in the day, was this ability to pipe output of one command to another, to another, to another, so you could do various things with it. Okay? Questions on that? All right. Let's go back to talking about the homework. So a bunch of people have asked, or a bunch of people have kind of said, hey, I'm not really figuring out this next free block. It's not actually, there are a couple places in the homework that I think people are having trouble with. This is one of them. Another one is making sure you return the proper pointer, or making sure you copy data from one place to another from like one location, say a new day that you've created, into your actual day list. You can do it using the copy assignment, which is just equals. If you say something like day list, I don't know, 0 equals, and then you've got another day in there, right? You could, if it was a pointer to a day, you would do this. You would say equals the pointer to, say, new day, right? And what would that do? That would copy all the stuff from your new day into your day list. If you forget to do this, then you're going to run into problems when you try to use your day list later. And you also, by the way, don't want to return the new day, right? Depending on how you do this, you can get away with it. But in general, return the actual thing. If you're going to return a pointer to something, don't return new day. Return, right, a pointer to your day list, 0, or whatever it was that you're trying to return to. Okay? So that's one of the things. That's not what I was planning on going over here. But that's one thing that I've seen a lot of people make mistakes on. They return the wrong thing, or they don't actually do the copying correctly. They kind of forget to do that part. And that's getting people's, that's creating errors that manifest themselves like farther down in your program, and it's tough to debug these things. Okay, questions on that? Be really careful with that. If you've gotten to a point where you're getting lots of bugs, be careful. Okay. So for this next free block of time, let's say you have a number of events in here, right? Event 1 and event 2 and event 3, like that. And you want to stick another event in here. There are definitely various cases you have to deal with, right? Like in some sense, you have to deal with the case where if you have an event and it's like before this one, then that might be a different case than if it's like between these two that you're trying to do, or if it's overlapping with one. What are some strategies people have used for finding the next free block of time? If let's say you've got your event that's like this one you're trying to put in. In other words, it does overlap with this one. New event. What are some strategies people have used? Ideas? Yeah, Ben.
Do you check if it conflicts, and if it does, change the time to...
Yeah, we've got a function that checks if it conflicts. I forget what it's called. But if you check this against this one, will it conflict? Yeah, but what if it's before? What if it was before this? Could you still go and check all these to see if they conflict? You could, right? You could, or you could make it a special case and fit it in there. Yeah, question?
That's the main problem. I didn't understand what type of list goes into next free block. Because if it goes before, shouldn't it have been scheduled in scheduled events? Why would it have a problem? Why would you have to find a nice free block for it if it went before the first element? Or
okay, let's say there were 3 elements already in your day. That's when if there are no elements in your day, and this is a proper event, it should go straight in, right? So that's maybe the first thing you could check. You could say if there are no items in your day yet, if the day list or day count is 0, sure, this one should go straight in. That does make sense. But if there are already events in here, then the schedule block won't do it correctly. It will try to put it right where it wants to go, and then that's it. So does that answer your question, or is that the beginning of your question? Okay. All right. So anyway, so you've got to maybe check here. Now, let's say that this one conflicts with this one. Okay. We've already said that part of the rules here are it can't go before its original start time. You can't move this and say, oh, it would fit in the day up here. We can't do that, right? Maybe in some other calendar we could make that a thing, but we didn't want to do that. So if it's going to go here, or if it tries to go here and conflicts with this one, where's the next possible place it could possibly go? It could go down here, right? It could go right down here, maybe, right? We don't know. So when I was doing this one, I said, fine. If I get a confliction, if I get 2 events that overlap, the first thing I'm going to do is make the start time of this one equal to the end time of this one, right? And then So then now it's going to be like that. And the end time of this one has to be correctly, the duration has to be the same. And this gets a little tricky because adding times is just inherently difficult, right? Because of the fact you have to wrap around. But once you do that, if you change this, now some people didn't want to do that. They wanted to go through the whole list. I think it's probably not a bad idea if you do this, and then now you've just changed your event to now be here, and you've taken care of this one. It will definitely fit here if this was the only thing in the list. What if it then conflicts with this one? What do? Same thing, right? Maybe you go down here. What if it didn't conflict with this one? Like, let's say that it like now fits right in here, right? If it doesn't conflict with this one, can we put it right there? Sure you can. Now that's another kind of, you have to figure out the logic to make that work, right? If you wanted to, and you wanted to be kind of more verbose about it, you could go and check all of these, and if you did it by move, if you didn't conflict, you left the event where it was, you could immediately stick it in at the end where after you get through all the other events checking them, and it would either fit in, or what's the one problem if it gets to the end and doesn't conflict with the last one? What's the one other thing we have to check? Make sure it doesn't run over the day, right? Because of the way we've made days, you can't have days, like you can't have an event that spans more than one day. Okay? So do you see how that's kind of the logic here? You go and you check each one and then make the event. And there are other ways to do this. You don't have to change the actual event times, but you have to keep an idea of where it is so that you can check both the events and know where to put it in if events don't conflict. Questions on that? If you're still having trouble with that after you look at it, do come to office hours, email me. We'll figure it out. The logic part is probably the hardest part of that. And then getting the details down about where to actually put it, kind of the other part. And then remember, you're going to return the right things and so forth. Next free block, actually, this one returns an integer to a time, I believe. Next free block does, right? So that will tell you where the next free block actually, the place where you can put this event. And then you can just update your event that you've got when you called the next free block function. Okay, questions on that? Yes, Ben.
Can we do it recursively?
Can you do it recursively? I guess you probably could. You can do a lot of things recursively. The only issue with recursive is, A, you have to break the problem up appropriately. You have to make sure you have a stopping case, and you have to do all the little details that come along with it. But I don't see a problem with that if you can figure the logic out, sure. Yeah, I didn't do it recursively. I don't think it's necessary, but if you want to, you can, sure. Yeah. Other questions on that? Any other questions on the homework itself at this point? No? You're all finished with it then? No. It's all right. We do have a few more days before it's due. Yeah, Peter.
Testing data now that's on or that you updated correct.
Yeah, so at this point, the output should be correct. Is correct as far as I'm concerned. The people who have finished the assignment, there are a few people who have finished the assignment, have done their assignments, and the output has been the same, and they've done the check. So I've verified that that's correct, yes. If you're still having problems like the infamous event 34, which a lot of people are like, it's not going in properly. I mean, first thing, go check your pointers again. Second thing, check your logic about how you're putting it into the day. But yeah, the output should be good. If you're still having trouble with the output, then maybe it didn't copy over correctly. A couple people that still didn't seem to work, they're copying right. Just email me, we'll figure it out. Okay. Anything else? No? All right. Okay, so that's homework 3, and we're getting there. Okay, it's like bad news today, right? Midterm coming up. Midterm is March 12th. Okay, you are going to be allowed a one-page back and front handwritten note sheet, kind of like you've seen in, I think, Comp 11. You're allowed something along those lines. You know, the worth of these sheets is more in the creation of them. I mean, that's what I've always found. You don't actually end up referring to it too often during the test. Sometimes you might, but put whatever you want in there. If you want to put, you know, how to, you know, what the big O notations are for all the different types we have, and kind of a little chart on that, that's fine. If you want to put a little C++ code on there, that's fine too. But you can put whatever you want. Let's see. There will be some questions about big O notation. I'll go over an example of that in a few minutes. Okay, you'll have to write a little bit of code. I'm not going to make you write like lots and lots of pages of code. A, it would be impossible to grade because there's so many different solutions to some particular problems. But I will make you write some code. Okay, if you would have done similar things in Comp 11, I think, maybe in 50. You'll have to find some minor bugs in code. So today's lab, Bruce has come up with an awesome lab for today. It actually involves anonymized code from homework assignment 2, which has some bugs in it that some of you guys actually created, and you have to actually sit in lab with some partners and figure out what the bugs are. That's the way lab's going to work, Bruce? Sounds right? So you're going to figure out what these bugs are, and then you're going to either code solutions to test them or simply say where the bugs are and what the bugs are. You'll have to do similar things on the midterm. Okay, so being able to read code is important. All right, and then as I said before, we're going to have a review class March 10th. So Monday will be a review class. And unfortunately, I have to be in Seattle all weekend, and then coming in on the red eye on Monday morning, so I might be falling over. I'll have a big cup of coffee, something like that. Anyway, that's that. Okay, so what are some practice, like what are some ideas of the types of problems that we have? I mean, this is the idea of the big picture, but let's take a look at some actual examples. This is from a previous year's midterm. Okay, take a look at this. To compute exponents, we can use repeated multiplication. This is an exponent function, right? Here's a simple function to do that for integers a and b, both greater than or equal to 0. I will try to spell out problems like this so that you don't have to worry about like corner cases and don't have to worry about the fact that there's, that integers might not be greater than 0. Okay? exp1, exponent 1, int a, int b, compute a raised to b. So far, so good. Okay? All right, so we have a couple of variables, z equals 1, y equals 0, a little while loop with a piece missing. Guess what you're going to have to do there? And then the actual loop itself and return z. Okay? Don't worry if you have to, if it takes a while to process this stuff, don't worry about it, right now processing it. But that's really what it's going to be doing. Question number 1, of course, is going to be what goes in that while loop? Right? Think about it for a minute and see if anybody can figure it out. It's not too bad. A raised to the b. Got a couple hands, couple hands. What do you think? Well, y is less than b. Is it less than or equal to? I know, you'd have to figure it out, right? You'd have to do a little test in your head and say, oh, that makes sense. OK, how did you come to that? Question 2 would be, describe your method for coming to that conclusion. It's a counter for how many times a is being multiplied, or I guess it's, a being multiplied by itself, right? Good. OK, so that's all you need. I mean, you don't need too much more detail than that. It's a counter, and it's going to, if you go all the way up to b, then it's going to be enough times to give you the multiplication. You might want to write that out a little bit. OK, let's see. What other questions would I have on this? What statement should go inside parentheses? Check. We did that. Explain how you determined your answer. There you go. Argue why this function actually returns a to the b. Now, you kind of just did that in the sense that you said, oh, it's a counter and whatever. But you could probably go into a little more detail and say something about how, well, a raised to the b means that it's a times itself b number of times. If you've got a counter that goes up this many times, then and you're multiplying a, then it will return b. If you look in here, or it will return the answer. If you look in here, z is what we're actually returning. That's what's getting multiplied. A couple sentences on this. Does not need to be a huge amount of writing for this, but make sure that we understand why you think it's going to return the value. Okay? And then this is kind of the big one. What is the running time of this function as a function of a and b in big O notation? That might scare some of you guys. We never talked about the functions and things, right? Break it down a little bit. OK. What is, first of all, for this function, OK? Actually, does anybody want to give me what they think? I'll give you a couple minutes to think about it before we actually go and give you the answer. Think about how you might figure out the big O notation of this. And remember, I do not care about the tiny details. I care about the big picture here. What's it going to depend on? Our big O notation. Yeah, question.
When you're answering this question, you say in respect to a it's this, and then in respect to b it's this?
No, I would do one function.
Okay.
like this. I would say the function of a and b, right, equals O of something, right? But you might want to actually fill in the details a little bit more in there before you do that, right? So you could say the function of a and b equals something equals big O of something, and we'll fill those details in a second. Okay? You might want to start by thinking, hey, let's at least count some of those operations, right, that we talked about in class last week. Count some of those operations. And I don't really care if you're off by one or so on the constants. In fact, this doesn't actually matter in the big deal. But for instance, int z equals 1. If you counted that as one operation, I'd be happy. If you counted it as two operations, I'd also be happy. I don't really care in the big picture, right? And I had this on the battery charge this morning, but I guess it's not going to work. So anyway, so you don't have to worry about those details, but you should give it a good shot on this one, right? Okay. The running time of thing. Okay, so first of all, well, anybody want to give me what they think it is, the running time of this? Big O of what? Big O of n. I don't see any n's in there. Oh, big O of b maybe. Yeah. Gee, you can put n, and I would probably give you some points. But in this case, it's got to be a function. In this case, it's a function of which variable are we given in here, right? B is the one that actually ends up being, because does the magnitude of a actually matter? How many a's we have? No, it doesn't matter at all, right? But so the function itself, okay, let's kind of fill in some of these details about the function itself. All right, how many times do we actually, or how many, well, let's go from the top. Let's count up. Are we going to count int z equals 1 equals 1 or 2 one or two operations? 2. We'll call it 2. OK. So there's going to be 2 for the first one. OK. How many for the second one? 2 also. OK. And then the while loop. How many times is that while loop going to go loop through? It's going to be b times, right? And how many? It's going to be b times. And then how many different operations are inside that? Yeah, you can probably get away with 4. I mean, z times a is 1. Setting equal to z is 1. Y plus 1 is another one. And then setting it equal to y is another one. 4. OK, 4. And then how many do we have at the end for the return? 1, although we know it's lots because you're returning. But we'll call it 1, right? OK, so then if we add all this up, what's the function of a and b going to be? By the way, a is not even in there. Doesn't actually matter, right? What's the function going to be? 4b plus 5. What do we get rid of when we do big O notation? Constants. Just get rid of them, right? That one definitely is not going to matter because it's less than b. And then the 4 is also not going to matter because we don't care about that. We end up with our big O of b. OK, see how that works? Not too bad. I mean, you gotta kind of do a little bit of pondering about what operations are going on here. OK, and I would expect something like that. OK, I won't ask you to do average cases. Like I want to know like the worst case in this case. OK, big O notation gives you the worst case for our purposes. Yes.
Do you know if you can count one for the comparison?
Which,
For the while?
oh yeah, you know what? We did forget about that one, didn't we? Yeah, there's one more for the comparison. 1, right? The comparison that we left blank up here. OK. Right, we're gonna put that in. You're right. That's going to be the comparison is going to be here, so that's going to be 5b maybe. Yeah, you're right. And then that would be 5, but we're still going to cross it out, right? Okay. Remember, the only time we'd ever really care about those numbers is if it was like zillions and zillions, right? Like the constant here. If for some reason this function had some other lots and lots of stuff in there, then it would actually matter. But it's not going to matter for our purposes. Yeah.
If you were declaring an array, would you have to declare, would the number be the size of the array, or would it just be like?
If you were declaring an array, would the size be, what would the size be? Count it as 1. Just count it as 1. I mean, honestly, it won't really matter. And I would never take points off if you said 4 versus 5 here. Because you can argue that, hey, look, z equals z times a. Yeah, that takes 1, that takes 2, depending on who's counting, right? If we're saying the return takes 1 operation, well, that's bogus, right? But it's not on the order of b, we're going to say, if b was big enough. OK? Now, here's another little kind of, remember that big mathy slide I showed you with the two functions, right? For this function, right, there's actually a fair amount of stuff going on for the first thing here. When you that second function that we're trying to find eventually ends up below the first function, there's a certain amount of time in here where it's definitely going to be higher because of the fact that return takes a number of steps, and you do have to set up the variables and all that. There's going to be a fair amount of time. I mean, if you're going to use this function and say 4 raised to the third power, right? That's not asymptotic behavior, right? 4 raised to the 4,000th power or something like that is asymptotic behavior. It's a behavior that's long term here. That's when you start getting your big O notation, right? Your O notation out of the function as you go farther and farther away. The constants and things all kind of get enveloped at the beginning there. It's like startup costs. Okay? Questions on that? All right. So let's see. We actually went through all these. Y is less than b. Explain how you determine your answer. We need to loop to stop computing when y equals b, right? When y reaches b. Argue y returns a to b. Well, look, z is multiplied a number of times to equal the number of times through the loop because the loop's executed b times, etc. We went through all this. Okay. All right. And then finally, the running time. Let's see. I counted 3. I didn't count int z equals 1 to 2 as 2 operations. I just counted as 3. But I got the same asymptotic notation, the big O notation, order of b. Questions on that one? OK. All right. Let's look at another one, another example here. So this is a recursive implementation of a function to search for a value in a linked list. Returns a Boolean value, et cetera, et cetera. All right. Explain 2 things that are incorrect about this, because there are a couple things about it. And then, will any of those problems cause a compiler warning or any errors? I want to know that too. Let's think about it for a second. We'll give it a minute or so to think about. Now, I'm not looking for very specific C++ things that are wrong. If I happen to have, I would not give you a question that had L list with 1 colon there. I'm not going to make you like parse through the C++ code to that extent. I'm kind of looking for bigger ideas here. Okay? Got a couple people hands up. You're going to answer a question? Answer, OK. Let's give everybody another second. OK, Vivek, what's one thing?
It's never going to find it.
Why is it never going to find it? Be a little more specific.
You never compare the part of the linked list with what you're looking for.
Yeah, you actually don't actually do the comparison that you need to for find it, right? To see if you've got the right answer. Good. That's one thing that's wrong with this. What's another thing? Yeah. You never actually return true. Yeah, that in this case you return false if you never find this thing, right? And in fact, the only time this would actually work is if you had no elements in your list, right? Because the problem is at the end there you've got search, find it, but you have to return the search if you're going to do that. Would either one of these cause a compiler warning or an error? Which one? There you go. The function reaches end of a doesn't return a value or whatever that one is. Yeah. I believe with the way we've set up our compile flag, it's an error actually. Yeah, I think it's an error. Maybe not. Maybe some people are saying no. Some people are saying no. Oh, all right, warning. Well, I thought it was one of those warnings that actually makes it stop. Maybe not. But anyway, it should tell you if you've got it set up right. That sort of thing should get caught. Okay. The other one, you never compare. Well, the compiler doesn't know what you're trying to do, like the logic behind what you're trying to do, and you haven't done anything other. You haven't the leaving out the actual comparison with the value is not going to give you any errors. Okay. Good. So you'd have to write those things down. Okay. Questions on that? Ideas of kind of how this test is going to be? We'll do more review on Monday. I just wanted to give you an example so you kind of had somewhere to start if you wanted to start studying this week. OK. Let's talk a little bit about binary search tree complexity. OK. We are talking about remember we always said we definitely want worst case behavior, right? We always want worst case behavior. We many times want average case behavior, but I'm not going to make you guys try to figure out average case behavior, except maybe in some very simple circumstances. Okay? But let's think about our binary search tree. Now we got to remember what our binary search tree actually does to do find min and find max. Okay, someone want to remind me, when you're doing find min in a binary search tree, what do you do? Yeah. Keep going left until you don't have any farther left to go, right? And that will give you the minimum value. Okay, so what is the complexity of that in an asymptotic sense? What complexity do we have for just a generic, regular old binary search tree? What's the best case? Yeah. The best case? Constant, right? I mean, you just all of a sudden found it, right? There are no, like the top element is your minimum element. If you had 1, 2, 3, 4, right? Well, you're starting to go boom, go left. Oh, we're done, right? So best case is constant, right? You just have it's the first one you get. Okay. What's the worst case in this one? Yeah. N, yeah, okay, so we keep talking about how great these binary search trees are, yet your worst case is on the order of n. Why could it be n?
If the tree went all the way to the left.
Yeah, if everybody in the tree was left, if this was the exact opposite, where it was 4, 3, 2, 1, you'd have to go all the way down all of them to get there. Okay, so binary search trees are not necessary, especially the ones that aren't balanced, don't have worst case complexity of anything better than n. You've got to do that. Now, it turns out that it's on average, it's going to be somewhere around, well, in this case, it's not even going to be log. I think it's going to be the square root of n or whatever, which we haven't talked about in terms of our complexity. But on average, you would expect that you're going to have to go the square root of the number of nodes to find the actual min. Okay, so all right, so it's order n for that one. Same thing for find max. Okay, how about contains? Do you remember how we found contains in a binary search tree, whether it contains a value? How did we do that? Yeah. Yeah, you compare nodes and then decide to go left or right based on that. Okay, what's the worst case scenario there? Or what's the best case there? If contains. Okay, we're trying to find contains 1 for this tree. Best case? It's the root. It's 1. Same thing. Order complexity 1. Worst case? Order n also. By the way, remember how I said this was just a linked list when we write it in this horrible, degenerate form when we insert these this way? Yeah, the reason we're getting all these order n's is because we can't create a binary search tree that ends up with these terrible conditions like this. All right? For the order n. And order n is not terrible, but it's not optimal. It's not as good as we might like it. Okay, insert. All right. Could we have to traverse the whole tree to do an insert? Sure, same deal. Remove. Do we have to traverse the whole tree to do a remove? Sure, we would also have to do that, right? We have to find it first, then you have to do remove. Okay? The actual finding is the part that's going to take the order n, right? And then the removing, well, remember we had a couple little things going on there. Are those really going to matter in the removal part of it? Like, in other words, is the fact that you're going to have to move a node here and switch a node here, is that going to matter if you've got a billion node list? Once you find it, that's the tricky part, right? Okay, so binary search trees. All right, worst case, not so great. Average case, pretty good. I'm not going to make you figure that out, but pretty good altogether. Okay. Does inserting into an AVL tree change the complexity of the operations, or for that matter, any of these operations, an AVL tree? What do we think about that kind of balanced tree? Is that going to help us out in this case in terms of our best case and worst case? What do you think? What do we say we have to do for balanced tree, for AVL trees, right? We have to make sure that they're relatively balanced, right? That was 3, and that was 2. Well, this isn't going to be a good example. Let's make it, 2, 3, 1, and we'll make that 4 and 3. There we go. Is it balanced according to our AVL tree? Yeah, it is, right? And what's the actual benefit we get from a balanced tree? How many nodes do we have to go down? At most, really? Log n plus 1, right? Log n plus 1, are we going to care about that plus 1? We're not going to care about this one. So AVL trees, much better situation, right? You can, if you've got the tree that's relatively balanced, your worst case in this sense is going to be order log n and then plus a little. So forget about that little, and we get the order log n. Does the fact that we have to balance every time, is that going to hurt us in the long run? What do you think? It's actually a pretty good question for midterm. Stomp my foot. Yeah?
Well, I think the benefits will outweigh the overhead costs that you have.
Yeah, it's all about overhead. It's all about benefits versus the overhead. Do we have, when we're doing that tree rotation, right, do we ever have to rotate, do we ever have to move on the order of the whole tree? We never do, A. The most we would ever have to move is half the tree, right? And you really are gonna do that in more or less constant time in the big picture. Okay? So balanced trees, very good. You do have the order log n in general for those, and non-balanced binary search trees. Well, you can if you need to worry about the worst case scenario, it is order n. Okay. Questions on those? Keep in mind. Well, this is actually leading into the kind of the next thing we're gonna talk about for a few minutes. Okay. All right, no questions. Let's go on to this other idea. So we've got binary search trees, and binary search trees are great and all. And we could do the AVL trees or some other balanced trees, and those are good, and those are log n behavior. But the question is, can we actually do better than a binary search tree for certain cases, like, for instance, looking through a dictionary or a dictionary words? And the bigger question is, do we ever care about looking through dictionaries for words? Ever used your cell phone and typed a text message and it like does autofill for you? Well, that autofill is comparing. It's got to compare. It's got to know all the words in the dictionary, right? And it's got to know at what point to suggest a word for you, right? And Apple or Google or whoever create the algorithms for this, they have to think about these things. They want it to be fast. They don't want you to like be typing a word, get all the way to the end of the word, and the algorithm goes, oh, I've got the answer. I know what word you're thinking of. Well, it doesn't really help you. They want to get it as quickly as they can, and in fact, as soon as they can make some sort of prediction as to what that letter actually is. Let's say we had a balanced binary search tree with some words. Okay, a relatively balanced tree with some words. Okay, it doesn't have to be perfectly balanced. Here's a bunch of words. I think I found these words on a 3rd grade word list or something like that. My nephew's word list. So here's some words, right? OK, so if you were to compare words and you were to use the binary search tree, well, we'll do it in alphabetical order, which I think makes probably the most sense in this case. OK, and I hope I did this one right. Yeah, I think I got this one pretty much correct here. OK, all right, for this, we've got order what to do searches for these words. If I want to find pits, P-I-T-S, right? Well, that takes how many different search looks, right? 1, 2, 3. The tree is 3 deep, right? So that, and the deepness of a tree is on the order of what? Balanced one? Log n, right? Keep mentioning that. OK, so we've got this log n business here. There are some places that we might want to think about compressing things, right? I mean, pit and pits, those are different by 1 letter, yet they each take up a whole node in our binary search tree, right? Cow and corn share 2 letters, right? Some of these other ones actually share letters. That may be important. Okay? But if you take this list, okay, and we say it's on the order of the total n. And in this case, what does n represent? What is it? Number of nodes, right? In this case, because we're looking at, say, a dictionary, what what is that number of nodes? What does that correspond to? Number of words, your dictionary size. OK, so if you have a dictionary and it could have like 1,000,000 words in it, right, you're going to need on order of log 1,000,000, which is not that big, all things considered, right? Let's see, log 1,000,000 is like 20 or something like that, right? So in base 2. So but you do need those 20 searches, and you need to carry all these things around with you, all these words around with you. And it doesn't really help that much in terms of if, depending on how you insert, you could have pit, and in this case, pit and pits is right next to each other. There could be a case where they're kind of far apart on the tree, depending on how you insert them into the tree, right? Just depending on which one happens to go which way. They're going to be somewhat diverse, not necessarily. I mean, you'll still find them, but you can do that. So anyway, on the order of the number of dictionary items. Okay. So we can search this tree in order log 2n on average. Worst case, we already said it's order n, not for the balanced one though. Okay? But there are a lot of words. In a bigger dictionary, there are a lot of these words that actually share what we call prefixes. Right? And the prefix is just the first part of the word. Lots of words share those things. Okay? We already mentioned those. Okay? Can we do better than log 2? Why did we say before that we were limiting ourselves to a binary tree? What was nice about a binary tree versus all those other trees that like fanned way out into as many nodes as we wanted? What was the nice thing about the binary search tree versus the other one? Yeah. You always know how many nodes you're going to have, right? Or how many children you're going to have. You're going to have a left and a right, or 0 or 1 of either. So that's kind of a good thing about binary search trees. If you have a search tree that is, or if you have a tree that's actually got like you don't know how many nodes you are, well then you're limited to doing things like using linked list or using that strange, oh, how many siblings do I have method or whatever. And it's not particularly efficient. Okay, it's not that great. But if we were to say turn this tree into a ternary tree, in other words have 3 per node, we would actually get it down to log base 3 of n, which is better than log base 2 of n in terms of the complexity. I know we're splitting hairs here a little bit, but log 3 is better than log 2 in that sense. Anybody have any concerns about that? Okay. All right. So, oops. We said this. We said the benefit of the binary tree was that we didn't have to worry about the unbounded fan out. But what do we know about words? What do we know about words that might limit the fan out? In other words, we have to. I'm kind of trying to get you to think about this a little bit in terms of what we're going to end up developing. But what do we know? What do we know about words? And you all sing a song about it. Words in general. As a song, if you're bad and you get stopped by police, you might have to sing it backwards. Which song? The alphabet song. Right. Okay, the alphabet song. So we know that there are a fixed number of characters in the alphabet. Right? For words, this is actually very nice. Now, we're going to talk about like 26 letters, so everything's going to be lowercase and all that. In today's world, we actually deal with letters that are not just A through Z, right? Actually, funny story. You guys know if I said A through Z, would that make sense to you guys? Who's the Canadian in here? I forget. We had at least one. Where is she? Oh, she's in the afternoon class. Z is like the last letter of the alphabet in like colonial, like British speak, right? I don't know if you knew that, but the first time I ever learned that was I had a Canadian data structure professor who kept talking about Z, and I'm like, we're all looking at each other going, what are you talking about? Z. Z, don't you mean Z? And he's like, yeah, Z. Anyway, so we've got 26 letters, right? In today's world, we don't really have 26 letters. We have lots of like different languages. You can, if you want to kind of shoehorn different languages into this picture, you've got things like umlauts, and you've got things like accents and all that kind of stuff. You need to expand it a little bit. But for now, let's just pretend we're just dealing with lowercase letters. If we were to do a tree like this, where one letter was per node, and your children could be any other letters, but only letters, how many different children would you end up having? At most? 26. Remember, the problem with a binary tree was that we didn't know how many we were going to be fanned out to be limited to. although 26 is actually a pretty high number, and if you want to do capitals, and if you wanted to do numbers, and if you wanted to do other letters, you'd end up being actually much bigger. It turns out that if you do that fan out with just the 26 letters, right, you can actually get away with hard coding those letters. Or if you don't even want to hard code them, you can do them in some other linked list. But the length of that list is going to be, the maximum length of that list is going to be 26 in the case of doing this. And if you've got a 1,000,000-word dictionary, 26, not the end of the world. Okay? 26 children per node. Okay? In other words, what we're going to do is we're going to use the fact that we do have a limit on those letters to build a better tree, and one that's based on just that prefix. And that's what these tries are all about, these things that we're slowly building up to here. Probably a little too slowly. Okay? What if we did it like this? Okay? The fact that we have a limit on the letters, what we can do is we can say, we have a tree that looks like this. If we're doing corn versus cow, right? Or cow versus corn, right? Each letter is a node, and each node has at most 26 children. And as you walk down the tree, you can end up getting to a position where you can end up branching just based on doing kind of the regular old comparison between characters. Now, by the way, let me step back for one sec. If you look at this, do we ever have to compare characters in this? Or do we compare full words? Or is that a trick question? We are comparing full words, right? And you look at the word pit versus fish, right? And you say, okay, look, fish is earlier in the dictionary than pit. Well, you did have to do a character-by-character comparison at some point, didn't you? If you're looking at the difference between pit and pits, and maybe a word pite or something, P-I-T-E, you have to compare at least a couple letters of that in order to do that comparison. We say that this is like, oh, we're not actually comparing characters, right? You are. It's just you're doing it at a lower level than you actually, might need to. Now, is it going to matter again in this big scheme of like asymptotic notation? Maybe, maybe not. But bear with me on this. Okay, so lots of words share prefixes. Okay, especially words that have like plural forms, right? I mean, everything's the same except the last letter or last two letters or whatever, right? If we set up a tree like this, okay, we actually call it a trie, and the reason it's called trie is because the guy who invented it said it stands for retrieval. Well, he said it stands for retrieval, T-R-I-E, and he calls it a tree. But then we also have these other trees, which we've been talking about the whole time. So most everybody else calls it a trie, T-R-I-E, so that we can differentiate it. But then there's various, well, let's call it tries. Okay? All right. So here's what we do. If we insert all those different words from before, this is what it ends up looking like. Okay? All right. We insert all the words, okay? The top node is just going to be an empty node, basically. It's just going to be the root. Okay, because it doesn't, it doesn't really, like, it would have to be, you'd have to have some sort of weird situation where you got roots that are all the different letters, and we're not going to worry about that. We're just going to have the root be up here, and it's going to fan out, and a maximum of 26 different letters, and you can kind of see how the words end up coming out, right? Pits is nice. It's only one straight down tree, P-I-T-S. The asterisks in here are how we designate where words actually end. Okay, so if you're looking for pit, right, you start going down, you go to the P, you go to I, and you go to T. Well, you can see, is that the end of a word? It is the end of a word. I have found my word, right? In this case, if I was looking for the word SA, which doesn't actually exist as a word, let's say. Although I don't know if you guys play Scrabble. You know those like two-letter words in Scrabble? Kind of painful. I don't know why they actually let some of those. Like AA is a word in Scrabble. I never quite understood that. But anyway, SA, if you're looking for SA in this, we have not put the word SA, if it exists, into this trie. And so therefore, when you go down and search for SA, you'll go SA, up, it's not the end of a word, so therefore I didn't find the word. See what I mean? So you can search for words that aren't actually words, and it will, if you have the mark for where it's actually a word, you will know that that's not actually a word. You can search for it, but it's not actually a word. Okay? All right. So you let's look at the benefits first. Benefits of a try. The benefits of the cost of looking up a word is pretty much fixed, right? You do not have to look through an entire tree to get to that word, even if it was logarithmic, right? You never have to go deeper than the actual word length. So especially for relatively short words, this is great, right? You never have to go deeper in the word length. It is not based on the size of the vocabulary. Why would it be based on this? Like your search doesn't have any reason to need to know that there's n different words in this dictionary. You're just searching down for the prefixes. In other words, you're just searching down the list until, and it doesn't actually matter how big the list is, because your word, if it's there, will be a fixed amount of steps away, not somewhere down the bottom of some tree. Okay? You don't even have to balance these things, right? These tries, you don't have to balance them because the max depth is based on the maximum word length. Okay? So if you have words that are 10 characters long, well, that's as deep as it's ever going to go, right? Because of the way we set this up. Let's talk about the complexity then. Okay. So what did we say it's not based on? N, the number of words in the dictionary. What is the complexity based on? If I'm looking for the word corn, right, what's the complexity of that search? The number of letters in the word. It's actually, the complexity is awesome. The complexity is actually basically order 1 in the sense that you need to look through the number of letters in your word, but the letters compared to the number of words in the dictionary, you're not going to have words that are like supercalifragilisticexpialidocious. You might have 1 or 2 of those words, right? But compared to the number of total words in your entire dictionary, you are not going to actually have to worry with it. It's actually maybe not O1. It's actually, I guess it would be OM, or whatever the length of your word is per word, and that's the complexity, right? But in the grand scheme of things, this is a pretty good situation. Okay? Doing searches and tries is great. Okay? I've mentioned this earlier. We're actually ignoring the complexity of letter comparisons in word-based binary search trees, right? You're still going to have to do the same number of comparisons in this case, right, for the letters. And you would have to have done those for the words too, if you were going to look for the words. They're hidden. Now you say, hey, I want to see an animation of this. And I went to that animation page, and I went and searched for tries, and it didn't show up. They hadn't created one. So that wasn't too fun. And then I searched for other try animations. Excuse me. And I couldn't find any. One was like some Java implementation that didn't work. And not to mention the fact that they used all these security functions for Java now, and it didn't work. So I had to build my own. So I had to go and write this. And yesterday I spent half the day writing this little thing. But what it is it's exactly like the thing we had before. Let me go back and just make sure we know what the words were. We'll put all the words in here. Where is it here? Well, here we go. Fire, cow, red, pit, corn. So we put fire in here, right? That's what your try looks like, right? And that's how. And the red is how we determine whether it's a word or not. Okay. Pit was another one. All right. And let's see. Cow and red. Oops. Cow and oops. And red. See how it's filling up? It's pretty easy to, like this one, we're just filling up the first little row here with the letters. So I haven't actually had any duplicates yet. Let's see. Pit, corn. Okay, now I've got corn. So corn will go in here, and there it goes. It goes and it actually branches out here and here. Okay. And then sand, day, snow, sand. Oops. Day. Goes in like that. Okay, we still haven't done. And then snow. Snow actually branched, right? Because you've got a branch there, and it's going to go down like that. Okay. And then pits and fish. Pits. And pits just increased by 1 down there. Now we have 2 words there. And then fish. And fish is like fire. It should branch off at the eye, and there it is. Okay. So now you've got this try. This is online if you want. Go to the website. You can play around with it. You can look at the code if you want. It's all JavaScript. By the way, there's also a C++ try implementation on the website that I basically stole from a really nice implementation, this one as well. But that's on there as well. Yes, question?
So does this mean that every node needs to have 26 pointers?
Yes. In fact, it does mean that every node will still have 26 pointers. We'll get to why that's not the biggest deal in the world. First of all, we can compress a binary search tree into this. This is actually compressed compared to a binary search tree because of what? Pits and pit takes up one more character, right? So yes, there are definitely there are trade-offs to this. But yes, every node is going to have 26 characters. And if we had uppercase and if we had numbers, it would be double and whatever. In the grand scheme of things, we're holding 1 million words. It's not going to matter that much. It will add up a little bit. And in fact, kind of the dirty secret is that tries do take up a little bit more space in general than a binary search tree because of the fact you've got this overhead. You could do it with linked lists, and each one would only have 26 pointers instead of 26 individual characters. But this is actually a fairly nice, actually it would only have 1 pointer, not even 26, it would have 1, right? If you did it right. You'd have to search through and do that. But so this is also an example of a relatively sparse tree in that there's not that many nodes. How many different Z's is each letter going to have, right? I mean, if it's a dictionary, the odds of you having lots of Z's as you go down is going to be very, very slim. Okay, you don't actually need that many. Okay, so it's a relatively sparse type of situation. Now, what can you do with this? You can search through here. Okay, so if I want to search for the word fish, right? Well, it'll actually, I couldn't figure out the animation quite properly, so I had to pop up this little thing. But it says found the word fish, and here's how it got there, right? Just did a little same idea where it does a comparison, character comparison, each one down. Okay? If I want to find the word fished, ED, right? Well, it'll try to go down there, but then it'll get to the end, and it'll say, oh, I can't go any farther. And so it will not find the word fished, right? And so on and so forth. It should stop when it gets to pit. If I'm searching for pit, it shouldn't go all the way down to PITS. So there you go. It searches boom, boom, boom. And you see how it's only doing the number of nodes that goes down is the word length. That's it. Okay, so it's limited in that sense. Okay, there are problems with my animation. If I started doing like, let's see, what's a good example? Coward. Nope, that's not a good example. Hang on. C-O-U-L-D, could, right? It starts branching out a little bit, and then C-O, what's another C-O word? Cold, right? Cold, yeah, oh, that one still works. So I think 5 is about the maximum you're going to get on some of these. And then, well, if I did cows, yeah, it starts to overlap a little bit, but oh well. You can shoot me now. Okay, so you can see how these are built, and you can see how they actually limit the number of nodes you have to traverse to actually search. It's a very cool data structure. Okay? All right. Let's cover a couple more minutes about a couple more things about that. Any questions on that one? So yes.
Yeah, what happens if you search for a word whose any letter isn't a specified any letter? Like if you search for fur instead of fire.
Okay, if I search for fur, it will get down to, and it says it could not find fur because what it does is when it gets to that end letter, it checks and sees if it's red, basically. And if it's not marked as a word end, then it can't be a word. So fur exists as a word. So I could then go and say, hey, wait a minute, it's not found in my dictionary. You can do that in your dictionary, by the way.
The R would turn to red.
I just put it in, the R turned red, and then we would search for it, and it would come out. Yeah, yeah. So fairly good data structure for this sort of thing. And in fact, pretty easy to insert into, too. All right? Inserting, same thing, the word length. Okay, removing words would be, well, about moving some pointers around too. It's basically, it's also order 1 as well. Pretty simple stuff. Okay, questions on that? Okay, all right, so let's go back here, talk about a couple more little things here. Okay, so benefits, limited on other characters. The fact that we do the limit is a better true based on the prefix of the word, which is cool. Okay, gone through the complexity. All right, I mentioned this a little bit a couple minutes ago. the actual space required to store the tree. You do get a lot of compression out of the fact that if lots and lots of words share prefixes, they get compressed down to basically one little tree until the end when they start branching out. Okay? And dictionaries are a very good example of that. Lots of prefix overlap in terms of dictionaries. Okay? They do take up, in general, if you're only storing one letter per node, well, that takes a lot of space in general. And if you have to store all those children nodes or pointers to all those different children nodes, it takes up some more space. So really, you're not gaining too much in space, but you're not losing that much either. In the overall picture, you're not losing that much. And what are you getting out of it? The ability to search in a constant time. That's the best part about it. Okay, it's great that way. Okay. And by the way, for something like this, how would your phone decide whether you wanted to type cow or corn? What kinds of things might it think of to determine whether or not if you start typing C, is it going to immediately say cow? Unless you type it like a million times in a row, right? And it's got some algorithm where it's like, how many times do you type cow? He always types cow, just cow, right? You're probably not, it's probably not going to say cow, right? But if you type C-O, well, maybe you would start doing that, right? Maybe if you type C-O-R, then it might say, oh, maybe, it might put up a little C-O-R. So there's algorithms they can use to do this, but the finding of the word that you're thinking of is very fast. And then you have to do some kind of artificial intelligence in the sense of, then you determine what some follow-on letters are, right? If you were to look at the difference between typing corn and corner, well, I don't know how many times you type either of those words, but let's say that somebody's done statistics on these things. And by the way, there's statistics on all of this stuff. Somebody's done the statistics on here to say, it looks like the odds are you're typing corn instead of corner. So I'm going to suggest corn after you type C-O-R, right? It'll start doing suggestions like that. But don't underestimate the power of statistics for this sort of, that sort of behavior. Being able to tell you what you're going to type in. Like cow a million times. All right. We can further compress this, right? If we wanted to, we could have a somewhat different scenario here where the only thing we actually keep are when you get to a leaf node, if nothing else, if it doesn't branch anymore, keep the entire rest of the word in that leaf. It's not a bad idea, right? Pits is a little weird because you've got to figure out where there's two words based on that scenario, right? But fire versus fish, if you can compress it a little bit more by doing this. Okay, sand and snow, you just keep that last little word in there. It will increase the amount of work you have to do at each node, just because you have to do some more comparisons and figure out at each node. But maybe you just mark each node that's a leaf as a leaf, and then you go into a different part of your algorithm to check it. You could do that. We could even do better than that, right? We could actually say, at each part that doesn't have any other branches, just ignore that node together. Like fish, if you look at the top one, right, the F and the I both have one character each. Well, but there's no branches off the F, so just combine anything that branches or that doesn't branch into its own word, and you could do that. Again, a little bit more complicated, but not too bad. And this tree is like super short now, right? You still have to do all those character comparisons for what it's worth, but you get the benefits of not having to worry about quite so much space. The problem, of course, then is how do you deal with all those nodes? Now, if you're going to have like a linked list based on the first letter of the word and so on. It's a little trickier. You can do it. It's a little trickier. Okay. All right. Here's another cool benefit of this. Okay. Take a look at this. So this is part of the C++ code for this try. Okay. When you are trying to search, okay, take a look at this. Here's what we do. We set up a current node. We set it equal to the root, and then it's just actually, this is an iterative approach to this. Okay, take a look at that highlighted one. Node temp equals current find child, and then you pass in the character. So in a node, we have to have a find child function, and if we do the find child function for the node that I've created here, take a look at how much code I have to write for this. Boop. This is kind of cool. This is like sneaky kind of C++ sneakiness here, okay? Not even C++, like just kind of using what we call an ASCII character set you can do the following. You can say, find child says, look, if we know there's 26 nodes, okay? It's kind of like doing those little ciphers you are as a kid, like the little Annie or little Orphan Annie like cipher ring, right? A would correspond to which letter or which number in the array? 0, right? And B would be 1, and C would be 2, and D would be 3, all the way up to 25, right? If you do it that way, you can actually do this, which is kind of cool. You can say, all right, if I know that a character, based on its alphabetic location, gives you a representation based on like 0 based, A is 0, B is 1, etc., you can do the following. You can say return children of the letter, which is an integer. In this case, it's the integer 99 in ASCII. And if you subtract out A, which is a character which has an integer representation of 97, that will give you, right? That will give you 99 minus 97 in here, which means we're going to reference location 2, which we said was the location for the letter C. So if we put a node there, that's actually kind of clever, right? A little nice, clever little way to do it. Okay, where you can actually, you don't have to go searching through each node to say, is this letter, is this the next letter, is this the next letter? If we're doing it in an array. If you're doing a linked list, yeah, you still have to go link by link by link. But that's the way you do it there. Questions on that? I know it's people are looking at it like, I don't get it. What are we saying here? Look, we're saying children is an array, and it's got 26 buckets, right? There's 26 buckets in that array. And bucket 0 is for the A character. B is for, or 1 is for B, C is for 2, etc., all the way down to Z being 25. Well, how do I find what bucket I need to grab from? Well, it's just the character C, which is our 99 in our representation of numbers, because we have to number the characters somehow, right? In fact, I've got a little, over here, I've got a little ASCII character thing on my dashboard here. I know it's nerdy, I know. But there, C is 99, and A is 97, right? And this is the order of all these characters. Like here, 0 is null, generally null, right? All these little special characters. This is back from the day where you actually had your character terminal like that had a little bell on it to tell you when something was done, right? You'd be doing your work, and all of a sudden go bing. You go, oh, my program's done. Well, it's because you had a bell on there that would actually ring, and that happened to be ASCII character number 7 was your bell, right? And you go up, and then all your special characters here start up here and go like this. And then finally, and then you get the numbers. And then finally you get to letters, and these are all the uppercase ones. Then finally you get to the lowercase ones, and they are in this nice alphabetical order. This wasn't wasn't random. Like people thought about this and said, let's put the letters like this, right? I'm not exactly sure why they put these other ones between the uppercase and lowercase. I don't know why they did that, but there might have been some other reason. Anyway, ASCII characters. Okay. Question on what that is now? I'm not going to make you like do it out loud, but yeah, go ahead.
You do have to make sure that they're all both the same case, though, right?
Yeah, you do have to make sure they're the same case. Yeah, if I tried to, my program would probably, well, I don't know if my program would crash if I tried to enter something with an uppercase letter, fire. Yeah, it's not even letting me. It says it's gonna say there's some error, right? Let's see, JavaScript console. Let's see. Hang on. Did it give me an error? I can't tell. Hold on. Can't even tell. Hold on. Fire. Yeah, it's not even letting me put it in there, I don't think. No. So yeah, it's failing somewhere, not even telling me why. But yeah, you'd have to make sure they're all lowercase. Okay, you can do that in lots of different ways, but you would have to do that, sure. You had a question? Yeah? Yeah, good question. How do you make your code deal with non-ASCII characters? Well, that's a long answer. There's a long answer to that. I mean, you probably wouldn't be sneaky like this, number one, right? You wouldn't quite be as sneaky like that. You would have to figure out how to map those characters. There's a thing called Unicode, which is the way it's kind of like the after ASCII. Now you've got Unicode, which is more or less ASCII to some extent, but then it's got lots of extensions, so you can have characters from all different alphabets, characters that you can have symbol characters from like Chinese alphabets and that sort of thing. It would be much harder than this. I mean, the bigger question is, how do you actually compare a Chinese character to an English character like alphabetizing. You just can't, right? So there's ways you have to deal with that, but it's sneaky and it's long and it's painful. But people with bigger brains than me have thought of it all. So there are ways to do that. Yeah.
The character char C is a variable, so it could be any character. Yeah?
Chars, yeah. So again, dirty little secret. Chars are actually, they stand for characters, right? But they are just the integers from 0 to 256, I think. Yeah.
What I mean is, in the face of char C, the actual value could be A, B, C, D.
It would have to be A with a, yeah, it would have to be A with a little quotes on it, yes. But that would be, yes, sure.
What I'm saying, as it is right now,
Uh-huh. Oh, yeah, you're right. No, you are absolutely right. You're right. You're right. Thank you. Yes, I was in this case, char C happens to be C. I was using C. I shouldn't have used C as an example. You're right. This could have been any other character. Yes. Yeah. You're right. This could have been any other character. In this case, I used C as an example. Probably a bad example. Thank you. Yeah. All right. Any other questions on that? Okay. I will leave you with this, which is actually too bad because there is a try, right? But anyway, Yoda gave me that. If you have any other questions, stop by. We'll see you at lab or on Wednesday.